All right, folks. Last time we, this is segment 2, section 6.2. Last time we were looking at sort of some big picture ideas about how to solve trigonometric equations. We introduced the idea of how the period of those functions starts to appear inside those solutions and how to come up with values within a certain range. We only got to some pretty easy problems. And so without further ado, I'm going to get over here and we're going to look at some that are a little more challenging than what we had done previously. So just one second. This is 6.2, page 4 now. Okay, so let's remember I said, okay, you have these linear methods. And I've got a whole page of them we could do, but honestly, those are the easiest kinds, and you will have plenty of, we'll see them because we have to, everything sort of breaks down to those linear methods at some point anyways. So let's go on to something where maybe we call this factoring, okay? These are factoring methods. And let me just give you a sample problem. This is where we, remember I said, well, factoring, kind of the way you think about factoring is you know, maybe a quadratic equation that looks pretty simple and you can factor with whole numbers, but that's not exactly what's happening here. What we're starting to see is situations where we've got mixtures of trig functions in some cases. So here's an example of a problem where that might happen. So let's say 2 sine of x times cosine of x plus sine of x equal to 0. Okay, so now we will look at better methods for dealing with these at some point, but for now, you know, what we've got in our toolkit is to look at, oh, and let me just say also that well, since we're going to do all real solutions to begin with anyways, I'll just say x in 0 to 2 pi. So we have to take that next step to figure out which ones actually fall in the right interval. So notice, I mean, this is a trigonometric identity. It won't really help us any, but sometimes these things pop up, and when you see them, you're like, I wonder if I can make that 2x or sine of 2x or something. But because of this extra sine of x, there's not a whole lot we can do. What we need to essentially do with any sort of algebraic technique is we need to create factors that have a single trig function in them, which is kind of what we've been doing with some of these simplification routines. Is we're like, well, let's just get it down to maybe just sines and cosines and try to limit the number of trig functions. Well, that's exactly why we did it, is because it allows us to solve these equations. So notice there's a greatest common factor between these two terms. And if you pull it out, you get sine of x, and what's left over is 2 cosine of x plus 1 equal to 0. And you know from the zero product rule that means either sine of x is equal to 0 or 2 cosine of x plus 1 is equal to 0. So let's deal with those individually. Sine of x equal to 0. Now, we know that solution. That solution happens to be, I think we've done it. Well, 0 is one of them, but also the supplement of 0, which happens to be pi, and all coterminal angles, which turns out that what you'll end up with there is really just every multiple of pi. But let me show you how that works. So first off, x is equal to the inverse sine of 0 plus 2 pi times n, and x is equal to the supplement of the inverse sine of 0 plus 2 pi times n. There's my principal root, there's my alternate root, there's the business for the period on sine. So evaluating these, I have x is equal to 0 plus 2 pi times n. So 2 pi times n. And on this one, you have pi minus 0. So you end up with x is equal to pi plus 2 pi times n. And you can combine these into a single statement that just simply x is equal to pi times n, right? And any multiple of pi, including 0. So from this branch of the factoring, you end up with two solutions, which we'll collect in a minute here. For the cosine branch, we have 2 cosine of x plus 1 equal to 0. And we talked about how to solve these sorts of problems. You know, you move over to the side, you do a little bit of linear algebra techniques, and what you'll end up with is that cosine of x is equal to negative 1/2. And so to get x out of that, x is equal to plus or minus the inverse cosine of negative 1/2 plus 2 pi times n, which the inverse cosine of negative 1/2, that's 2 pi over 3. So we have plus or minus 2 pi over 3 plus 2 pi times n. And we don't have the numbers just staring us in the face, so we got to do a little, but this is all the solutions, right? And if we wanted to write that as all the solutions, you would say, well, x is an element of the set. And I'm trying to remember what notation they use, because it looks weird to do this. Maybe if we do something like a change in variable. So if we go x is an element of the set theta such that theta equals pi times n, where n is an integer, together with the set theta, where theta equals plus or minus 2 pi over 3 plus 2 pi times n, where n is an integer. Now that's kind of an ugly mess, but that does tell you all of the solutions, both this branch and this one, which is why I don't really favor these kinds of things, because really what I'd like to know is that people know what what values are in there. So I'll kind of do it over here to the side. X is going to be in one of the elements in the set, 0, pi, 2 pi over 3, and then 4 pi over 3. And that 4 pi over 3 might be a little confusing because that comes from here, where you take negative 2 pi over 3, which is outside of the interval, and you add 2 pi to it, you get 4 pi over 3. So here's all of the solutions to this equation in the stated range, 0 to 2 pi. Okay, so kind of a long problem, and they can sometimes get that way, especially when you're just first doing these. So let's look at another one. I think we're on page 5 now. Okay, so let's do one that's kind of a little bit similar, maybe a little bit harder to factor. 2 sine of t times cosine of t plus 2 sine of t. Ooh, that's looking real similar. But now we're going to have a minus cosine of t minus 1 equals 0. Okay, so if this was in the form of 2x times y plus 2x minus y minus 1, it might be a little bit easier to see what's going on. But I would say anytime you've got 4 term, I mean, this is not some super complicated course, and so they go back to some pretty standard techniques. When you see 4 terms, you should be thinking factoring by grouping, because that's one of the ways that, you know, kind of, I mean, you don't have a whole lot of techniques for 4 terms, unless there's some way to simplify this expression using our trigonometric identity sort of skills. But this one is pretty easy to factor using grouping. So you take the first 2 terms and you find their greatest common factor, which is 2 sine of t. And then what's left over is a cosine of t plus 1, okay? And then this second term, the greatest common factor here is just -1. Remember, if there's a negative sign on the leading term, you always pull that one out. So we have negative cosine of t plus 1. And notice now we have a binomial that has a common factor. And so to completely factor this thing, we have cosine of t plus 1 times 2 sine of t minus 1 equal to 0. Of course, the spin equal to 0. Okay, so now we have two factors, and they're equal to 0. Each one of them produces its own set of solutions. So the first one, cosine of t plus 1 equal to 0, implies that cosine of t is equal to -1. So t then is equal to plus or minus the inverse cosine of -1 plus 2 pi times n. The inverse cosine of -1 is actually pi, so this is plus or minus pi plus 2 pi times n. That's the solutions to this first factor. The other one, 2 sine of t minus 1 equal to 0, well, that leads to, I'm doing some of the algebra pretty quickly here, so that leads to sine of t equal 1/2. So x will be equal to the inverse sine of 1/2 plus 2 pi times n, or x will be equal to pi minus inverse sine of 1/2 plus 2 pi times n. And you know, you could break this down further, but since we're trying to find, well, inverse sine of 1/2, that's pi over 6. So maybe I could just rewrite them here. X equal pi over 6 plus 2 pi times n. A third branch is 5 pi over 6 plus 2 pi times n. Okay, and so now if we try to find all the values that work, note that there aren't necessarily, we don't actually get any unique solutions from this. There's only one angle, and it's coterminal angles, because if you take plus pi, how is that different from minus pi? Well, they're coterminal to each other. So there's really only one answer in the specified interval that comes out of this branch. Usually there's two, but the bottom line is x is going to be is a member of the set that contains pi, or pi over 6. Well, and it contains them, and 5 pi over 6. So this is the so-called solution set for this problem. Let's jump to maybe one more. We don't need to do a ton of these. And when I do this in a traditional lecture, I have way more than I actually do. Sorry about that. Okay, so let's look at this one. This one involves kind of a function that we don't do a lot of. How about cosecant squared of x minus 4 equals 0? Okay, so this is one of those kind of trick factors, right? This is something squared minus something else squared. And so the factorization of that is the first thing plus the square root of the first thing plus the square root of the second thing times the factor square root of the first thing minus square root of the second thing. Okay? And you know, we don't work with cosecant a whole bunch. You could turn this into a sine problem, but I mean, there's no need to. So we've got two branches here, cosecant of x plus 2 equal to 0, which gives you cosecant of x equal to -2. So x is equal to the inverse cosecant of -2 plus 2 pi times n. Now, this occurs, cosecant of -2 occurs at the same angle where sine is -1/2, which is actually negative pi over 6 plus 2 pi times n. But remember, cosecant has the same kind of weird branching that sine does. So we have to also say, well, x is equal to the complement of this inverse, this particular angle. So pi minus inverse cosecant of -2 plus 2 pi times n. And again, this is going to be pi over 6. So this whole thing breaks down into 7 pi over 6. 7 pi over 6 plus 2 pi times n. Okay, so that's the first factor. The second factor is going to look very, very similar, except that instead of being inverse cosecant of -2, it'll actually inverse cosecant of 2. And so without actually redoing all of that stuff, I'm just going to write down the answers because I do know how that works. So x is equal to pi over 6 plus 2 pi times n, or x is equal to, in this case, 5 pi over 6 plus 2 pi times n. Those are all of the solutions to this problem. Notice there are 4 unique angles and then all of their coterminal angles. So if you want to just find everything between 0 and 2 pi, then x is going to be a member of the set that contains, so this first one, well, negative pi over 6 isn't going to work, so we add 2 pi to it and we get 11 pi over 6. That will be in the right interval. So 11 pi over 6. For this one, 7 pi over 6 works. For the third one, pi over 6. And then finally, for this one, 5 pi over 6. We haven't, and for the most part, for each one of these sort of sets of equations, until you get to tangent, you'll see, well, I don't want to make that statement. I will show that later at some point. So I know the video is getting a little bit, I mean, this one's a little bit shorter than maybe the ones previously, but I think this is all of the factoring kinds of exercises I want to show you. I will come back and show solutions using quadratic methods next, and then maybe do a little bit of some side work, maybe something that's back to degrees, just so you remember how those work too. So I will see you in the next segment.